Hey everybody, it's Mark. Welcome back to another meta career questions. So we're still on level two, um, and we finished two here. I'm still working on this one. As usual, it's dynamic programming, and I think this one is also dynamic programming, and they're very similar. So hopefully, when I finish one, I can finish the other. But it's resulting kind of difficult, so I moved on to the later ones for now. So let's start with portals. So portals is very easy. It's pretty much just a what is it? Breadth first search problem, or a graph problem, shortest path problem. So this is about navigating your way through a maze, and evidently you can make a maze into a directed graph, right? Um, and then look for the shortest path using Dijkstra's algorithm, I think it's called. But when I was solving this problem on LeetCode previously, I found there's an even easier solution. You don't need to make a graph. You don't need to use Dijkstra's algorithm or anything like that. What you can do instead is, so you start at your start position. So let me show you what it looks like. So this is our maze. Our start position is S right here, and we're trying to get to the exit. Actually, there can be multiple exits. I didn't know that, but is that right? Yeah, I guess there can be multiple exits. No, there's only one exit. Wait, E is the exit, right? Yeah, there is at least one touch cell, so there can be multiple exits, which is fine. I solved it without even knowing that. Doesn't even matter. But um, yeah, you basically you start at S, and these are walls. The hashtags are walls, so you're just walking along the path until you finally get to that. So the way to solve this without making it into a graph, so you could make it into a graph. You could make every single spot a um, you could make every single spot a node or a vertex in a graph, and then you could connect them to the other nodes if they're right next to each other, because you can only move left, up, and sideways. And then when you're creating the graph, you would also always have to check, whether the place you're trying to move to is out of bounds, or if it's a wall. I mean, if it's a wall, it shouldn't really belong in your graph, etc. So those kind of issues, very easy to resolve, but requires some coding. However, you don't need to make it into a graph. What you can do instead, and you don't have to use Dijkstra's algorithm, what you can do is instead is just, since each movement is exactly one step and you're trying to minimize the number of steps, what you can do is you can just do, basically, you at your start position, you have a list of moves that you can go to, and then for all of them, you make exactly one move. And then you add all possible moves from those new positions, and then you repeat the process. So you do exactly one move for every single place for every single new place. So in that way, you're expanding where you can get to, um, one move at a time. And the first time you find an exit, that is the shortest path to an exit. Why? Because if there is another path to an exit, that means that you haven't, that it would take either the same number of moves or more moves. Because if it were to take fewer moves, then you would have already found it in a previous iteration of that thing where every single loop iteration, so basically what happens is every single loop iteration, you increase your radius or the distance that you allow yourself to travel by one. So then, if you found an exit, it is if you the first time you find an exit, it's optimal, because if it weren't optimal, if there were a solution that you could move fewer steps, then you would have already found it in a previous loop iteration. Hopefully that makes sense. Therefore, that is pretty much just exactly what it did. The twist with this problem, of course, they would try to make it tricky. They added portals. So when you enter a portal, you can exit out through any other portal in the map, um, that has the same name. So for example, in this example, A is a portal. So when you go through A, you can exit out of any other A. In this case, you have two A's on the same side and two B's on the same side, and you start at S. You start at S. So this is clearly impossible, because I mean, if this A were on this side instead, then you could jump across the wall through A, but since the A's are on the same side, it doesn't help you jump the wall, right? So that's why the return value is -1. It's not possible. So, yeah, I think, like I said, also the other thing is, once you've already visited a place, or once you've already considered it, and looked at it, and it's not the exit, then you can mark it as a wall. Why? Because backtracking doesn't help you in any way, right? If you've already, if you do this thing where you grow by one step every single time, and you've retraced your steps back to a place where you already were, there's no point considering that path because you've already reached that way with fewer steps, right? The fact that you've already seen that place with fewer steps means that it's not optimal, that path which you're looking at right now, to backtrack to where you were already at before. So if you try to move to a place where you've already been, you sort of disregard that move. So I have this function here called sanitize moves. So I have some new moves, and I did have to leave the portal moves out of here. Why? Because the moment I enter a portal, I add all the possible places where the portal goes to, and then I immediately add a wall there so that you can't just hop between portals, right? Hopefully that makes sense. Because you could do that infinitely. You could jump to one portal and then jump to another portal, jump to another portal. That doesn't make any sense. So the moment you enter a portal, you delete it from. I also have a dictionary for portals here. So this is a portal is a lowercase letter like this, and then the dictionary is a map between the lowercase letter and the I and J position of every single portal. So when you enter a portal, then you look at the map, you get all the places where the portal goes to, and you add those as new portal moves. So hopefully that makes sense. I think it's once you know how to solve it the first time, I knew how to solve it immediately, so it was pretty easy. So let's go to the next problem that I did, which is this one, rabbit hole. So this is also, I've actually also solved something similar to this. So let me give you an example of the way this works. So here we have, let me get the exact example, 4121. So what is this? So this is an encyclopedia, and this is page 1, and this is page 2, and this is page 3, and this is page 4. So what the objective of this, let me just say, so page 1, so what does this 4 mean? This 4 means that on page 1, we have a link to page 4. What does this 1 mean? So every single page has a link to another page. Link to page 1. Then this one has a link to page 2. And then this one has a link to page 1. So what is the objective? The objective, this one took me quite a long time because I tried to make it really efficient, and that made it much more difficult to solve, because there's like in array operations that you can do to make it so you don't have to use extra memory, or you don't have to use extra memory, because the size of this array is huge, 500,000, right? I mean, that seems pretty big. So what is the objective? The objective is to find the page, you don't need to know which page it is, but find the page which allows you to look at the most pages. Look at the most pages. And what do I mean by that? So if you start at page 1, which is this one right here, if you start at page 1, this has a link to page 4. So what happens when you read this page 1, then you go to the link to page 4, you go to this page right here, and then on page 4 you got a link to page 1, so you go back. So what does this mean? This means that you started at 1, you went to 4, and you went back at 1. So the number of pages that you can read starting at page 1 is 2 pages. However, if you start at page 3 instead, then page 3 has a link to page 2, which has a link to page 1, which has a link to page 4, which has a link to page 1. And this is, you can read 4 pages. So we're trying to find what is the maximum number of pages we can read. So in this case, it's 4 pages. If you try any of the other ones, you will get a value less than 4. So this is the maximum number of pages we can read. So like basically, we don't really care which page it is, but we just need to know what is the maximum number of pages we can read starting from the correct page. Max number of pages to read. So as you know, from group theory. I'm sure we all took group theory in college, right, guys? What this is a permutation, right? And it's not necessarily, I mean, I forget what the terminology is, but it's not necessarily a perfect permutation. I don't know, a group, or I don't remember the terminology. What I mean to say is that here like in this example, we have we have a page that points to 1, we have a page that points to 4, we have a page that points to 2, but we don't have a page that points to 3. And so, I mean, so the way I originally, when I looked at this problem, I was like, aha, I just need to find the, we have, so imagine we're a perfect permutation. Like, let's just say, imagine it's 4 and then 1, 2, 3. So each one of these has, when you start at any page, you go through every single page. So what I mean by this is that you can access, so every single page has a link to it in another page. That's what I mean to say. So every single page, all of these numbers are unique. Or they don't necessarily, so they don't necessarily have to be unique. So so this is an example of what it could look like as well. And if you start any page, then that's fine. But it could also look like this: 2, 1, 4, 3. And in this case, there are 2 cycles here, right? If you start at 1, you go to 2 and you go back to 1. If you start at 4, you go back to 3 and then you go back to 4. So there are 2 cycles here, and on whichever page you start, you end up. So there can be lots of cycles. However, in this example, right, what happened here is in the original example that I had, 4, 1, 2, 1, 4, 1, 2, 1. There was a cycle between 4 and 1. So 4 goes to 1 and 1 goes to 4. However, when you start at 2, 2 goes to 1 and then 1 goes to 4, and then you enter the cycle, right? So 2 is clearly the best one. However, so then based on this line of thinking, I was thinking, okay, here's what we need to do. We just need to find the number that has the that has nothing pointing to it, right? This is what and this is wrong, by the way. So wrong, let me write wrong, bad. We need to find the number that has nothing pointing to it. This is bad. Let me cross it out. Why? So let me give you a counterexample. So the counterexample looks like this. So 1, and let's just say 1, and then let's say 4, 5, 3. This is a counterexample. So, so 2, right? Has nothing pointing to it. And it immediately goes to 1, and then it stays infinitely in 1. So if you start at 2, you get to see two pages. Start at 2, you see 2 pages. Which sounds good, except when you try one of these later ones, you start at 3, you get to see 3 pages, right? So there's nothing pointing to 2, but if you start on this perfect cycle here that loops around to itself, so 3 goes to 4, 4 goes to 5, like this, then you get to see 3 pages. So clearly this strategy does not work, right? Bad. Bad. Very bad. Does not work. So, I think you will have to, I don't think there's a way to avoid having to look through the entire permutation. So here is my algorithm. 4, 1, 2, 1. So my algorithm is kind of, so if I were doing this as a human, right? Let's just say I start at the beginning, right? I'm going to try following this path, right? I'm going to try following this path until I get to a place where I've already been. So I followed this path, right here. This is great. So then I can probably count also how many times how many places I've already seen. Let me erase this. I can't. It's fine. So how many times, how many arrows I've followed? I've followed 2. Therefore, this permutation has a value of 2. And then I can keep track of like a max permutation variable, and then set this equal to, max of itself. and then this new permutation, which is 2. And then I could keep going through the array, see if there's another permutation. So let me think. What did I do? Let's see. Yeah. So that's all fine. Wait, what did I do? Good question. Oh, that's right. This is what I did. Okay. So look. So in this example, right? I'm looking at 4 and I looked at 1 and I figured out that if I start at 4 and I go to 1 and I get back to 4, this permutation has size 2. It's a cycle of size 2. It doesn't necessarily need to be a cycle, as I showed you. If I start at 2, right, I go to 1, I go to 4, and then finally I enter the cycle between 4 and 1, but there's no cycle involving 2. So it's not necessarily true that the number that you start out with is you're gonna loop back around to it. You might loop back around to a later part in what you're looking at, but not necessarily the start. So what happens when I find another 4 here? Let me show you what happens. So what I do is, let me see. It's kind of complicated. So this is, yeah. So first of all, I need to determine, so there's a couple things I need to keep track of to keep track. Number one, have I seen this place before? Have I seen this place before? And this is kind of difficult to track. I don't want to like use any memory structures outside of what I already have. Therefore, the most efficient way to do it is to modify the array in place. So how do I do that? When I've already seen a place, I set its value to negative value. So if I start at 4 and I go to 1, the moment I jump to 1, I set the 4 to -4. Okay? And then when I look at 1 and I jump to the next place, the 1 pointer, which is back to -4, I set this to -1. And then the moment when I see a minus, when I see a negative, then that's when I say, I've already seen this place before. I've already seen this, and I exit. So that's how I find my cycle. Okay. Now, so having gone through this cycle, I know how long it took, how many steps. So I know how many steps I had to take. However, what I don't know is whether this, well, I kind of do know, like okay, let's just say instead I started at 2 and this 2 were negative and this -1 were negative. So I don't necessarily remember how many steps it took to get to a place where I have a cycle. Hopefully that makes sense. I do have to end up in a cycle. You can easily prove that you eventually have to end up in a cycle. Why? Because this list of places is finite. And if there, there's no, you're going to eventually run out of places to jump to, right? If it's finite, therefore, eventually you'll end up at some place where it's a cycle. So now I know how many steps I have to take, but I don't know where does my cycle start. So that is the next question I try to answer too. Where does my cycle start? So why do I want to answer this question? Let's just say in the future, like when I get to 2, right? I don't want to have to look again. I don't want to have to follow this path again where I start at 2, I go to 1, I go to -4, and then I go to -1. I mean, that would be the easy solution. But that's super inefficient if I have to check every single place. What I would rather do is I would rather say, I'm at 2, I try -1, and then I go to -4. However, I've already seen this -4 before in a previous iteration of my loop because I've already followed this path from the -4 to the -1 to the -4, and I already know how many, what the permutation is for if I start at -4. I already know like how many places. So if I start at 2, and it takes me, and I see 2, and I mean, if I start at 3 and I see 3 and then I see 2 and then I see this thing here, the number of places that I can visit starting at 3 is equal to this place, plus the number of places I can visit when starting here. Hopefully that makes sense. Therefore, I want to have this value already saved in my, saved somehow, so I don't have to recompute it, so I don't have to follow the permutation again. So that's why I want to answer this question. Where does my cycle start? So what I want, the purpose of this, I want to end up encoding into the array how long the permutation is, how long, or how many places, how long permutation is. So basically what I want to end up with is somehow I want to, well, I can show you how I end up storing it. So n is the biggest value that the array can go. So what I want, basically this is what I want at the end of this one loop iteration. So I can access 2 places from starting at 1 and the same starting at 4. So because there's a cycle there. So what I want is I want to store n plus 2 plus 1, 1, 2, n plus 2 plus 1 after after I'm done with this loop iteration. So this is great. So why? And then if I, in a future step, if I go from 2 to 1 and then I see something here that's bigger than n, then I can say, oh, I've already been here. Let me take this thing here and subtract n plus 1, and I get 2, and that tells me how many places I can access from this without having to follow this again. Hopefully that makes sense. So this is what I want. And how do I do this? I'm going to add this information in like this, so that later when I accidentally travel to this place again and see this n, see this value that's bigger than n, I can subtract off n plus 1 and end up with 2 and say the number of places I can visit from this point is 2 plus 2, which is 4. And then over each loop iteration, as I told you again, I keep track of this maximum. And then at the end, this will be the biggest 4. So there are 2 encodings. Well, number 1, as I'm doing this first part of this loop, I'm setting the places I've already visited to -1. Then the second thing I do is I have to find out where does my cycle start. That's pretty easy. I'm going to basically start again. So I'm going to have to do like three loop, or three. I have to follow the arrows 3 times. So the first was to find, to set all of them to -1. And then the second time is to find the first time that we end up at -4. What I mean by that is the first place so when we did this first time, we ended up at the reason we stopped is we found a negative number. So what does that mean? That means that is the first place where we have retraced our steps. So in this second step, we want to find out where does my loop start. And how do we do that? We find the first place where we retraced our steps, which is exactly where we ended up with after this first step. So this is the first time that we end up at -4. So what does this tell us? This tells us, if we started at some place that isn't in the cycle, like the 2, imagine instead of starting at -4, we started at 2, then it would take us 2 steps to go to, we can measure how many steps it takes us to get back into the cycle again, into this -4. And then once we reach this -4, right? What does this mean? So we know how many, how long the cycle is, which is 2, and then therefore we can assign permutations. So this will have a permutation of 2, and then this will have a permutation of 3 because this one leads to this place, and this one will have a permutation of 4 if we started instead at the 2. In which case this would also be minus if we started at the 2. So step 1. set them to negative to show where we've already been before. Then that helps us find out where our cycle starts. Number 2, how many steps does it take to get to where our cycle repeats? And then the part 3 is this encode information about how big the permutation is. Encode information about length of permutation inside the array. Inside array. And hopefully that is enough to solve. So you can see this is the step 1. It's so messy, but we have to like set to -1, and it's kind of confusing. This, like I told you, if we see something that's bigger than n, I told you we've already seen this place before. We know how big the permutation length is, so we subtract n, and then we add how many steps it took to get to that place, whatever. So hopefully that makes sense. Those are the 2 problems I solved. Thank you very much for stopping by. I'll see you next time.